yeah, I'll move that. Okay, so quantum mechanics operators, let's start. Last time we reviewed that if you do a measurement, then it's very, well, to get a certain result of the measurement, you need to have your wave function, an eigenfunction of operators. Say we consider operator A, arbitrary momentum, kinetic energy, potential energy, right? And to get the kind of certain result, that means if we do thousands of measurements of the same system over and over, or to avoid any interference, we could just prepare the 1,000 copies, yeah, and then measure single one of them, right? So then, if the function that we are working with is an eigenfunction of operator, then we get one particular value, lambda, which corresponds to eigenvalue of that operator, right? But more interesting, the situation is when the A psi is not equal to lambda psi, so the psi is just some arbitrary function, and it's not an eigenfunction of operator, then we have a whole spread out. In this, if we do millions of measurements, we can have, well, the number of results for each particular value of lambda. Say it's a discrete set of values, right? Then we'll have the distribution. And there are two important characteristics of any distribution. One is no average value, right? And another is standard deviation. Okay, we will talk today about standard deviation a little bit because there is a nice relation that connects standard deviation of two non-commuting operators, A and B, say. So if we do sigma A and sigma B squared, then this quantity should be always more or equal than 1/4 of average commutator of A and B. Just move this. And that should be squared, okay, with I here. Okay, so that's the relation I'll talk about today. And what sigma A is, let me just define. You probably remember that from the statistics or similar course. All right, so what we do usually to calculate the deviation from some average value, right? We take A, we subtract the average A, and then we square it, because without square, when we average, we won't get any non-zero value, okay? And we need to square it and then average. So right now, I'll be using actually both symbols for averaging, the upper bar or the brackets, okay? So depending on the functional form, one or another way will be more convenient. So essentially I can write the same thing, that is a square of this quantity. I can write the same thing in terms of A minus A bar squared and then extra bar, okay? Or A minus the brackets. So I will be switching between those two. They are the same, essentially.
Dr. Ismail,
yeah.
Sorry, so what is A? Is that the expectation value? Or the
Okay, so what is A bar, right? That's
well, A and then A bar. A bar is just the average?
That's right. A bar is an average and A is an operator. Okay? So we will be talking about some abstract operator. It can be momentum, kinetic energy, any operator, right? And then A bar, which is the same as A in brackets, it's the integral over spatial variables, psi x star A psi x, right? So that's the quantity that characterizes the distribution of values which we obtain if we measure function psi, the property A, and we will measure the whole set, or like do millions or a big number of measurements, right? And we'll get the distribution, and that will this quantity will predict what will be the average of that distribution. So
I'm familiar with this. I just mean for the standard deviation when we just have A, like just without a bar on top.
Without bar on top, well, we need to calculate essentially. This is a deviation from the average, right? And then we square this quantity. Otherwise, if we average a non-squared quantity like this, we'll just get A bar minus A bar, or yeah, and that will be 0, right? Because the deviation from, oops, downtown. Do you still hear me? Because they disappeared.
Yeah, we hear you.
We hear you.
You hear it? Can you see the board?
Sort of, yeah.
Okay, I stopped seeing you. So if you have questions, please just interrupt me whenever it's convenient. Okay, so that's why we have a square there. And now we, yeah, so that's the meaning of the square. And now if we want to get the sigma A, then we take a, well, this is still operator, right? So we need to average it and take a square root to get the sigma A instead of sigma A squared, right? Okay, and that quantity characterizes how broad the distribution is, right? From essentially how far the ends of this distribution from the A bar, okay? And we talked at the previous lecture that if two operators commute, A, B commute, then you can find, and that is essential, that you can find a common set of eigenfunctions, right? It's not that they always, well, any arbitrary set of eigenfunctions will be a set of eigenfunctions for both operators, right? But you can choose, or you can find a set that will be satisfying these relations, okay, for the commuting operators. Now, if they don't commute, what we have is we have some sigma a's which are non-zero. And I guess the missing element here, which I want to emphasize, is that when they commute, your function can be chosen to be an eigenfunction for both. And in this case, sigma of A or B will be 0 necessarily, because if you create millions of copies of eigenfunction, of the same eigenfunctions for A and B, then when you measure A or B on that function, you will get only one value for A and only one value for B. Okay, if it's a not degenerate case, and let's assume that it's not, right? So then we will have only one value for A and only one value for B. And then the average of A will be that lambda n, and average for B will be theta n, right? And then the deviations, they simply will be zeros. There is a simple way to show this through the following algebra, if it's not yet obvious. All right, so this sigma A square is essentially, if you do again the average, A minus A squared, right? Then you open the square, you get A squared minus 2A A bar plus A bar squared, and that's squared, right? And then what you have is A squared average minus 2A bar plus A bar squared. Okay, so then we can well, remove this, guys, and the result will be A. Okay, so here A squared averaged minus A average squared. So this is the result for the sigma a squared, that means that when we have an eigenfunction to put here in averaging, then what we will get is Fn, our eigenfunction. It's also eigenfunction of a squared, right? It's just we act with a twice, right? And that will be just lambda n squared Fn. And the same thing we'll get if we just average first and then square. All right, so this value will be just 0 for the Fn. Okay? So for eigenfunctions, the sigma a and sigma b will be zeros if those eigenfunctions are indeed eigenfunctions for both a and b. Okay? Now, the situation when they are not, so the situation when a and b do not commute, right? We have this useful relation where we can estimate the deviations for a and b based on this quantity, 1/4 of integral over dx phi of x, right? And then there will be I commutator of a, b, phi x, right? So this will be a quantity that you always can calculate because, well, you usually know a and b and psi's, right? Then you can estimate what will be the product of these two deviations, square of deviations. Okay? So the way this expression can be derived is actually using the positivity of scalar product or dot product. So before we said that, okay, the way we introduce the dot product between two functions, say phi x and phi x, right? And that's the, in the Dirac notation, psi phi, right? This is our form, and then for any psi, this will be more or equal to 0. So there's this positivity condition for any scalar product or dot product, right? We'll be using that because the way we will prove that sigma squared are larger, the product of sigmas are larger than this expression, is through the following functional I of lambda. So we'll create the following functional that will always be positive. That's the main point here. So what we will do, we write the I lambda as the following expression. Here, delta A plus I lambda delta B, okay, psi star, it's for the whole thing, and then there will be delta A plus I lambda delta B psi. For consistency, let me put it like this. Okay? So as you can see, just in a second. So as you can see, what we do here is we take this complicated operator.
Would we be able to interrupt you for 1 second?
Sure.
Okay, so we're all watching you on a very small, I would say 17-inch TV or something like that. It's very tiny. And we actually can't see anything when you write on the right-hand side. Like, you can only just barely make out when you write on the left side. So, like, you know, we can do it for now, but, like, would you be able to just keep it to the left for us?
To the left.
Yeah.
Okay, can you see my hand here? No? What about here? That one? That's the only? Or Up to here?
See up to the line.
We can see basically into the line, yeah.
How about...
You see board that over in the middle. That's it, unfortunately.
can you see now the right-hand side?
No.
No, it's like reading like subscripts.
Okay.
Very tiny.
All right. You know what? This will restrict me quite a lot, actually. So I can just suggest, why don't we work on visuals between now and the next lecture, and for now we'll just cancel lecture downtown, because that kind of probably will make it hard for the undergraduate here to understand it will be a lot of essentially erasing and not much time to write things down and tell the physics. All right.
First lecture. So I watched your first lecture.
Yeah.
Online. It's gonna also be uploaded online.
That's right. That's what I'm saying. It's going to be available online, and so right. So that's right. So sorry about today. It's just it seems that technical people they didn't know that I'm going to be presenting on the blackboard, so they didn't figure out exactly how it's going to be projected. But right now it seems like it's going to be hard to fix this problem during the lecture. Okay. Okay. So send me your user IDs and I will add you to the list of people who can watch online webcast. Okay. All right. All right. No problem. Yeah. Sorry about that. All right. Okay. So now. This is the scalar product, okay, and then the delta operators that I wrote here, let me clarify what I mean by them. The delta A is A operator minus its average, and the delta B is B operator minus its average, okay? So why is it a functional? Because it's a map between a function psi and actually a number lambda back to numbers. Okay, we take psi, right, and we take lambda, and we generate a number with operators A and B acting in this way. Okay, so it will be clear why did we build this. Well. Main reason is that I lambda is always positive, okay, and we will use that. We can differentiate now I with respect to lambda, right, make it 0, and the lambda conjugated also will be 0. So when we differentiate, we will find lambda which will minimize I lambda. So I lambda is going to be something always positive, and we will try to find lambda that by making I lambda smaller still keeps it positive, okay, because by definition I lambda is positive, okay. And so differentiation that can be done here will generate the following expression. It will be delta A operator squared plus lambda squared delta B plus cross terms I lambda. Sorry, this let me our path. But this is continuation of what I lambda is. If we open up now the the scalar product, right? Then we can just the first term will be average of delta A squared, right? We've assumed psi's here, and then delta B squared will be the next term with lambda squared, because these two essentially generate delta B squared, plus I lambda multiply by psi delta A commutator with delta B. Okay, so that's the expression. Okay, now why do we have commutator here? It's relatively easy to see because one I lambda goes to the bra, another I lambda goes to the ket, and if you account for this conjugation, one I lambda term will be, say, delta B, which comes from the bra, will be with minus sign, then we'll multiply in delta A in the ket part, right? That will be with minus sign, but I lambda delta B from the bra part, multiplying delta A from the ket part, that will be with a positive sign, right? So I lambda is taken outside, and this delta A, delta B, they are in a different order, and with a different sign, we'll create the commutator.
Wouldn't the I go away, though?
I will not go away for the following reason, is that in a scalar product, if we have I lambda, say some function, and then we have some other function, we can multiply our bra part with some constant that will be minus I lambda if lambda is real. Right? We conjugate, right, and we can take it out, right? And if we do the same with the psi part, then we're taking it out without conjugation. That's just the definition of the scalar product or dot product, right? In a space where we can have complex coefficients. Okay?
Okay. No, I get it now.
Yeah? Okay. So we do that, and now we differentiate because we have a form that if we differentiate, it's like a quadratic form with respect to lambda, we can differentiate it, right? And we can get what is the lambda that minimizes the I, right? So the derivative will be, or essentially the equation for di with respect to d lambda equals 0 is equivalent to 2 lambda psi delta b psi and delta b squared, okay, equals minus I psi delta e delta b. Okay. All right, so now from this it's easy to see that lambda is actually minus I and then psi delta A delta B divided by okay. So that's this simple expression, and then we put this lambda that minimizes our I functional back into the I, and we write I lambda minimum, right? So this is equal to we have double I's. Minus I squared Okay, so we have 3 terms, and now we can simplify, and you already can see that we have delta b squared averaged in the denominator, right, of 2 expressions, delta a squared averaged here numerator. So and these commutators that we were looking for, well, not yet, but one thing I can say from the beginning here is that delta a, delta b commutator is the same as a b commutator. That's why the numerator, yeah. The thing. Can you see like this? Okay. All right. So this is true because the only difference between delta A, where is it? Yeah, delta A, delta B's, and actual A and B's, these constant terms that they always commute with everything. Constants commute with everything. So that's why we have delta A, delta B commutator the same as A, B commutator, right? So what we do then with this expression, we put these 2 terms to the right hand side, multiply by this term, and we obtain the expression that is almost like the one we were looking for. So this is say psi delta a squared psi more equal than, okay, so this I square becomes -1, this I square becomes -1, right? And so we are losing 1/2 then because of the different signs, and we get 1/4, and we get, since they are with minus, right, so then something like 1/4 of okay. Sorry, I was too early to remove the i's, and what I forgot was that these guys, they are, this is okay, and in this we have squared quantities, okay, here, and then if you do everything correctly and put this lambda into the expression, then that expression already had the commutator of delta A and delta B, so then the commutators will be squared, and let's just keep i's for now, because then we can put them inside of these squares. Okay, and so we will get 1/4 of I inside of the squares, and then psi delta A, delta B squared, right? And then this is still divided by psi delta B squared psi And then when we take this to the left, we'll get this delta A squared averaged, delta B squared averaged, 1 equal, then 1/4 of I. Here we have delta A, delta B averaged squared. Okay, and then since the commutators of delta quantity is the same as commutators of operators, so we can write the final expression. Okay, and these guys are sigma A square, sigma B squared. Okay, that's the derivation. It may seem long and difficult, but really it is quite simple. Once you understand the structure, you build something that is positive, then you minimize it with respect to parameter, because you know no matter how far you go minimizing it, it will still be positive, and that positivity allows you to formulate essentially the inequality for the quantities of your interest, sigma A and sigma B. Why did I go through the whole derivation? Just to show you actually that there is another interesting inequality that can be derived in the same way. That's why kind of going through this procedure, we're getting two inequalities for the price of one. And the inequality that you can derive in a similar way is so-called Schwarz inequality, also very important for quantum mechanics and other areas, because you generally what you have is if you have function phi and function psi, right, two different functions or two different vectors, then Schwarz inequality tells you that the absolute value of this will be always smaller or equal to the square root of phi square and psi square. Right? So how can you derive this? It turns out you derive the same construction. You take phi, but no complex algebra here. You just take the constant which is real, phi minus a psi. Maybe I should have started with this inequality to illustrate the principle. The idea is absolutely the same. So let's say we have a lambda alpha functional, right, or a function of alpha, and this function is always positive because we have the same vector, right, or the same function Brian cat, so it's always positive, right? And then what we do, we differentiate lambda with respect to alpha, find alpha minimum, and that alpha minimum will be, I have it here, I think Tanner has it. Essentially, it is psi phi divided by psi with positive. Okay, so this is alpha minimum, and if you put this back into the expression, use this condition, then you will have a relation that will end up essentially in the Schwarz inequality. Okay, and geometrical meaning of Schwarz inequality is also quite simple. If you think about these functions as vectors, right? So say vector phi and vector psi, right? So then their product, this dot products, and square root of them, it's essentially the length of phi multiplied by length of psi, and it's always bigger than this scalar product. And we know from just the simple analytical geometry, or I don't know, vector calculus, or not even calculus, but vector math, is that the cosine of angle between two vectors, right, is a scalar product of phi psi divided by their norms, which are the square root of, these guys are essentially square root of phi. Okay? And so the Schwarz inequality tells us that cosine of theta, now if we take the absolute value of cosine of theta, right, it's going to be between 0 and 1, right? So this means that numerator will always be smaller than denominator. Okay? Doesn't really matter what quantities you are considering, vectors, functions, as long as you define a scalar product, then you can well, build some order in your space, okay? And you can get these inequalities, which become quite convenient in calculations, because in the many-body problem, say if we consider molecules, an electronic structure, which hopefully we'll get at the end of this class, there are integrals like so-called two-electron integrals. Okay, and those are complicated quantities, and there are lots of them, so it's actually a big problem to calculate them. So say you have some functions phi, j, r, and I'll tell you in a moment how Schwarz inequality can be used to reduce the number of integrals that you need to calculate. Okay, essentially what we have here is an electronic structure. You represent all electrons as orbitals of single electron orbitals, right? And these two electron integrals, they describe the Coulomb interaction between two distribution of charges. One is, say, product of phi I orbital with a phi a orbital. That's one distribution, and another distribution is phi j orbital. And,
so are we trying to find the likelihood that the electron will be somewhere? So like the expectation value of the position or something?
This is more like from the Coulomb energy of interaction of two electrons. One is represented with this distribution, and another is represented with this distribution.
And what does the integral, when we calculate it, what does that tell us?
The integral? Well, the integral is, well, generally integral is needed to obtain the contribution, right? The average of any operator. In order to get a number out of it, you average it with a function, right? So now imagine the A here is the Coulomb interaction, r minus 1 over r minus r prime.
So that's our, okay.
Right? So that's what appears when we consider energy of the molecule, right? And we describe every electron as a single electron in a single electron basis. Okay, this basis of orbital, they form distributions. I'll describe this more in details later. The main point here that is even in such complicated and seemingly unrelated integrals, you can still use Schwarz inequality, because this this operator, they also form, they can be thought as like a scalar product between two distributions, essentially. Right?
And just one, so
Yeah.
we're setting, like in the Coulomb interaction, we have like the charge of the electron,
Mhm.
epsilon naught. We're just setting that all to 1.
Yeah.
Oh.
This is not essential. The essential part is that we have many pairs like this and like that, and the question is which ones do we need to calculate, right? Because this is what essentially makes the calculations difficult. And don't pay much attention to the kind of details. Of course, I don't provide enough here, but what you should be able to see is the usefulness of Schwarz inequality, because essentially this integral can be thought as a scalar product of two distribution IA and JB through this Coulomb metric, right? So it's not only the distance between the distance between the distribution is weighted by this Coulomb interaction, but other than that, if this is positive and if this is non-zero and this is non-zero, then you will get positive element, or if they are the same, right? So then you definitely will get a positive element, and that allows you to estimate this IA-JB contribution, the absolute value of it, right, as again square root of IA term, and then JB term, right? So then the number of terms like this, they grow only like a square of the size of the system, because each index runs, say, from 1 to, well, n, right? And then since these two indices exactly the same as these two indices, right? So number of such integrals is proportional to n squared. Number of such integrals also, well, essentially proportional to n squared, while number of such integrals are proportional to n to the fourth. All right. So if n roughly is the size of the system, then you can remove some of the integrals, and you don't need to calculate all this. This is 6D because each r is a three-dimensional quantity, right? So you can remove some of these integrals by doing the so-called Schwarz screening. If you know that this guy is small and that guy is small, then you can estimate that this one will be also small. Okay, so you can remove some of them like that. That's the use of Schwarz screening. All right, and
I'm still a little bit confused. We have on the slides like phi sub I, J, A, and B, and what do those represent? Like they're wave function systems, so like.
yeah,
So like for example, we have phi sub A conjugate and phi sub B down there.
Mhm.
What is that representing?
these functions,
Yeah.
they represent, say, approximate basis functions of the way we want to represent the electronic wave function of the multi-electronic system, right? We represent it as a Slater determinant of these functions phi I. So we have a product which is anti-symmetrized. So we'll go over that once we get to the molecular systems, right? So here, the point is not what exactly these functions are. The point is that you can use Schwarz inequality even for such quantities which are not directly, well, kind of connectable with the normal, just the integral of two functions. There could be some other extra kind of, in this case, Coulomb metric, essentially, right? That weights how close the one distribution to another is. As long as everything is, well, staying positive for diagonal elements, then it means we can use this as a new definition of scalar product. And once you have a definition of the scalar product, you can use Schwarz inequality, right? Okay. And so that just to show you that well, Schwarz inequality can be useful for things that are beyond simple overlaps of the functions, okay? And that's used in the electronic structure calculations a lot. All right, now, another. interesting relation will be about average, like essentially averages of operators and their time dependence. So say we have an arbitrary function xt, right? That is a solution of Schrödinger, time-dependent Schrödinger equation. This is a, and h depends only, say, on x. This is just a normal setup in any quantum system. If you consider its wave function, it must satisfy time-dependent Schrödinger equation, right? The same is not true for time-independent Schrödinger equation, right? So this is a big difference between time-dependent and time-independent, is because not every function of x will satisfy time-independent Schrödinger equation, right? But if you there is more freedom in time-dependent equation if you start with something that is normalizable and describes your system. It doesn't need to be an eigenfunction of time-independent equation. It can be a linear combination, right, of the solutions. And this is not.
Why do we not get that freedom for the time-independent equation?
Oh, because it's eigenvalue problem.
Okay.
Okay, and this is a first-order differential equation in time. It's essentially you give me a function at time 0, initial conditions, right? And then this equation will tell you what this function will be in time t.
How it evolves.
Right? How it evolves. It doesn't really care whether this function, the initial conditions, are an eigenfunction of any operator, right?
Yes.
So it can be anything as long as it's normalizable. You can go, right, and solve the time-dependent Schrödinger equation for that initial conditions, right? In that sense, it's less restrictive, and essentially that's closer to life, because in life, in order to have dynamics, you need to be in some kind of superposition state, right? So then things are evolving. Now, if we ask the question, say we calculate some operator on that function, right, on psi. Right? And if we ask ourselves, what will be the time derivative of this average? Because psi over t, it potentially can depend on time, and a can depend on time. It can be a time-dependent operator, right, generally. So this quantity, since we integrate only space variables, can be a function of time. And the question is, can we find its time derivative? If we can, then if this is some kind of function of time that we can calculate, well, then we can obtain, by solving the differential equation, what will be the evolution of average, right? And there will be a big value of that. So let's see, can we do that? Can we derive something for this quantity? It's also called in physics equation of motion, right? Because it's an evolution of the average quantity. Mm-hmm. Now, if we just apply d over dt as a to this integral, all right, then we will have three terms. First will be d psi over dt, a psi. Then we'll have psi, and then dA over dt, psi, and then okay. Now,
It was probably just a little mistake, but the first derivative that you have there, should that be partial?
yeah, so they all
Partial.
partial, although you see there is a difference here between quantum and classical mechanics, because in quantum mechanics every quantity has a partial, well, we have partial derivatives in time because x doesn't depend on time, while in classical mechanics, position of the particle can depend on time. So it has a time dependence, right? So then there's a point of writing or separating partial and full derivatives. Here we wrote the full derivative because kind of like operator can depend on time, psi can depend on time. And then later we kind of, all these quantities have only one time dependence through time, right? So there is no need to do the chain rule differentiating first with respect to x and then with respect to x with respect to time, right? So there is no hidden time dependence. That's what I'm saying. Okay, so now we can just say that this quantity is the way it is because it really depends on the way the operator depends on time. So there's nothing we can do. Depending on operator, we will deal with that quantity. There is no more simplification we can do here, right? But for these two quantities, we can actually apply Schrödinger equation for this directly, right? For this quantity, it is will be only thing we need to do is to divide by IH bar, right? And it's 1 over IH bar, H of x acting on psi, right? And for this quantity, it will be a negative 1 over IH bar because it's for conjugated or because it's for bra part, right? And then it will be H psi H, right? And then the final result can be formulated as d over dt equals to bar this one will go with minus, so let me write then A H minus H A psi, oh, plus here, right. And then plus dA dt, right? So then d over dt equals to, if we do I H bar, then this goes back to HA commutator, right?
Plus the partial.
Plus the partial, yes. And so this is essentially equation of motion. Okay, and why is this important? It's also sometimes called Ehrenfest theorem. Okay. Why is this important? Well, it tells you if, say, A is just a function of x, right? So the partial derivative is gone. Then it tells you that if A commutes with a Hamiltonian, then there is no time dependence of average, right? It's 1. Then d over dt is 0. And second, even if it doesn't commute, Okay, then if you have a stationary state, usually that, well, you still can have no dependence. For the reason is quite simple. It's that the Hamiltonian commutator with A is just with some functions, right? So even if this is not 0, then the average can be 0. Okay. And now another interesting consequence from this, just to illustrate the second point, if you take say harmonic oscillator case, and there H, and say take A equals X, right? Hx is up to the constant proportional to P, because H contains both T and V, right? T contains P squared, and P doesn't commute with X, right? So then commutation relation of P squared with X gives you P as a commutator, and then it seems like commutator is non-zero, but if you take psi, which is a ground state of a harmonic oscillator, say some Gaussian, right? Then, because of the symmetry, right? So P is is operator that differentiates. So when it differentiates a function, then it creates a node right in the middle. And so then the integral of the psi with the differentiated psi will be 0. Okay, so this is a Hx essentially is equals to 0, and this is the reason why, if you consider the average value of x, it doesn't move anywhere.
So this commutation relation between the Hamiltonian and the position, in general, is proportional to the momentum.
In general, you mean for molecules? And
Yeah,
for
well, we're not talking about any specific wave function. Like that is always true regardless.
That's right. Yeah.
But for us to use this equation of motion, right, Ehrenfest theorem, we need to calculate the expectation value. Sorry, I'm walking myself through
That's right. Yeah.
logic. And to calculate the expectation values, we need to choose a particular wave function. And so in this case, we said when we're considering quantum harmonic oscillator, then we're going to find that the equation of motion will be 0 for the operator we're positioning.
That's right. That's
okay,
right.
so in order to use this equation, we need a particular system.
That's right. That's right. And more than that, if you consider stationary states, then your quantities will always be, like these averages of A will always be time independent for the A's which are time independent. So let me clarify this statement. Now imagine third case, we consider A, though we already have this, for A equals AX, right? And then we have psi, which is a stationary state, right? So it has a spatial part, and then the kind of the time dependence will necessarily be ENT divided by h bar, right? That's what is true for the stationary state of the Hamiltonian. Okay. Then if we consider the commutator of H, A with psi, right? This is integral. We have phi n star x, okay, and then h a minus a h, and then there will be, I forgot the positive exponent, right? And then here there will be phi n positive exponent minus, right? So then this will be just en phi n, and this one will be phi n star en, right? And then what we have is dx. Then these guys are gone. They are, well, essentially simply the conjugated quantities, right? So we have exponent with plus and minus, right? So they cancel each other, and we'll have phi n star a with the en minus, essentially, a minus a en phi n, right? So this is en squared in both cases. No, not squared, but just the en, and then a minus a, which is 0, right? And so this is d over dt for the a. So if you have a stationary state, right, it doesn't need to be an eigenstate of a for the average a value not to be dependent on time. Okay, it's stationary for an arbitrary operator that is time independent. Okay, and for the same, well, for this case, I guess the example of the harmonic oscillator is also relevant, because in the harmonic oscillator example, we take an eigenstate of Hamiltonian, and what we find is that although the commutator is not 0, the average of the operator is 0. All right, or time derivative of average is 0. Okay, so then another interesting consequence of this Ehrenfest theorem is attempt to connect quantum mechanics with classical. And this expression here allows you to do that in the following way. So you probably heard about the Hamiltonian equation of motions, right, for the classical mechanics. And the equations are, say, if we have a classical Hamiltonian function of q and p, where q is a position, p is a momentum, right, then what do we have? We have q dot equals to dh over dp, and then p dot equals to dh over dq with minus sign, right? So these are the classical Hamiltonian equations of motion. Well, quantum analogues of that would be d over dt, and q dot is dq dt, and p dot is dp over dt. The dots in classical mechanics usually mean the full derivatives. Okay, and now the kind of quantum analogues. This equation would be, if we try to find what will be the time derivative of the q operator or x operator, doesn't really matter. Q is equal to x, right, the coordinate. And from the Ehrenfest theorem, we know that it is I divided by h bar, average of h, and then here it will be q operator, right? Now h over q, the commutator of hq, should be proportional to p, as we were discussing, because generally the only part that is not commuting with q in h is kinetic energy. Okay? So this will be, according to my notes, you can check this at home by doing the commutator. It's a minus IH, and then here there will be P, right, instead of commutator. If you do the commutator, right, there will be P operator. And then we can write by putting back IH bar, and then dq over dt equals to P operator. So this looks like, in this case, the classical analog of that will be if we consider h to be t plus v, while the t is p squared divided by 2m, right? And so dh over dp will be simply p divided by m. And here I lost m. It should be divided by m. Okay? And when we differentiate t with respect to p, we also get p divided by m. Okay? So then the classical analog would be q dot equals p divided by m. P divided by m is velocity, right? And q is velocity for simple systems where the kinetic energy is just a p squared divided by 2m, right? And so the quantum analog is very similar. Here we need to operate not just with q and p, which are operators, but their averages. Okay? So this is very simple and nice, right? Now with this part, it's a little bit more difficult and doesn't quite work out for all the potentials for the following reason. So if we consider this, then we are getting dh over dq. The only part that depends on q is v, right? So we have p dot equals 2 dv over dq with minus, and this is a analog of Newton equation, right? So this is acceleration multiplied by mass, and this is the force, right? Now what do we get in the quantum case? We have d over dt for the p quantity, and it is equal to the corresponding commutator that essentially gives you something like dv over dq, but the averages are for this operator. Okay, so I'll need to put IH bar here. Yeah. So from the quantum HP commutator, you will get the derivative of the potential with respect to the position. Okay, and you may say that, look, this is pretty similar to the classical expression, right? But the significant difference here is that the correct classical expression should be the following. So it should be p dot or dp over dt with IH bar equal to minus dv calculated on at the point of the average q divided by the average q, differentiate with respect to average q. Okay? So our v of q derivative, okay, we can expand it in Taylor series, right? And the first term would be around this point. Here we essentially what we do, we expand the function in Taylor series and around the point which is the average of q value. And this is the integral over psi x q. Oh, okay, so q is x, so we integrate q psi q. Okay. And then the other terms will be like in a normal Taylor series expansion, q minus q average, second derivative of v at the point of q, okay, plus third derivative. Do you understand what I'm doing here?
You're just writing the derivative, or just think of it as a function, you're just writing it as a Taylor series about the point of the average?
That's right, that's right. And so what am I trying to do is I'm trying to substitute this quantum expression by its classical expression plus some quantum corrections, essentially.
From the classical version, how do we get the expectation value, like the average value of the position? Why does that show up in the classic? Like that, no, that's the quantum mechanic, right?
This would be a classical expression. Okay.
Why does it have IH bar?
Sorry, the IH bar should not be there
Okay.
because it should be absorbed. Probably what it should be absorbed into P in the both cases. Right. So it should be absorbed in P and should be absorbed in P as well here. So yeah. I guess you can see that if you do the commutator carefully, not like I just put the proportionality to P. So IH bar should disappear. Right.
So basically, from quantum mechanics, we get the partial, so the expectation value shared.
Mm-hmm.
The partial of the potential energy with respect to whatever we're calling our position, our generalized position.
Mm-hmm.
But classically, we get the partial of the potential energy with respect to the average value of our generalized position.
So in classical analog of quantum mechanics would operate with Q average and P variables, and once we average them once, right? So then we can use them as just numbers, right?
Yeah.
Right. So then, what prevents us to do that is this part, where for the Q we can for the Q and P the first equation is perfect. We have this as a number or a function of time, and this is a function of time, right? And so we can keep going with the classical mechanics. Just once we obtain them for initial conditions, then we can propagate them classically according to this equation, right? Now, when we go to the momentum, in order to propagate these two quantities, Q and P average as a function of time, we need also the time derivative of the momentum, okay? And so time derivative of the momentum ends up being an average over this force, okay? Where we want it to be like this quantity, where we can just put the Q average and put it in the potential and differentiate with respect to it, right? So that would be ideal classical equation of motion for P average dot, right? And in order to get something like this plus quantum correction or quantum force, I would say, quantum force, yeah, that depends on quantum force, because the true P dot average is this value, right?
Yes.
Is this equation. And this equation, using the Taylor series expansion for the V derivative, right, for the force,
So we get a
can be presented as a classical force plus this part, which is a quantum force, right? And so what I'm trying to do here is to show you what will be the quantum force, what's quantum correction.
Does that have measurable consequences? The quantum force, like, can we measure this quantum force? Like these
We can definitely propagate or observe the evolution of P as a function of t and the Q as a function of t, where we obtain them solving either classical equation of motion. By classical equation of motion, I mean without the quantum force correction. And we can obtain them using the quantum equation of motion with quantum force. Okay?
And that turns out to be correct. That matches what we observed.
Yeah. That will be full quantum. That's what we observe if we can do that for a system that we're observing, right?
Yeah.
So, but the main point here in this Taylor series expansion is that if you now consider, since we're interested in average of this, right? So the average of this function will be the function. The average of this thing will be, this is a function again, but this, you average Q and you subtract the Q, which is already average. So this will be 0, and this will be just a constant of some kind, second derivative, right? But it doesn't matter really because you already have multiplication by 0. And the only non-trivial part will be coming from here, from the averaging of this, and this is kind of a deviation, standard deviation of Q from the average Q, okay? And it also has a multiplication by the third derivative of the potential. So that means, first conclusion, is that for the potential, like a harmonic oscillator potential, kq squared divided by 2, where the third derivative is 0, classical and quantum equations of motion will be the same, right? That's why harmonic oscillator is somewhat simple problem for considering, especially if you're interested in quantum effects. Doing the classical approximation and testing them in harmonic oscillator may not be such a good idea because everything works for harmonic oscillator, okay? But if you have some potential, general potential, where you have the third derivative is non-zero, then you get the correction due to these quantum terms.
And so,
Okay.
do we not use terms higher than the third derivative? Like, is that just where you decided to stop? And then
No, you can go more. This is just the first correction from the quantum mechanics in this expression.
and you can add more terms if you want to be more
Right.
precise. Okay.
That's right. Yeah, so you can go to the fourth and higher. Right. So the main point here is that we have classical mechanics if our potential has derivatives only up to the second one of the potential with respect to positions. Okay? All right, so now another useful relation that we can extract from this Ehrenfest theorem is so-called Virial theorem. Yeah, quantum Virial theorem. And that is the relation between potential and kinetic energy. Yeah, let's do our kind of few minutes break. So last topic for today, Virial theorem. It also comes as a result of using Ehrenfest theorem for an operator A, which is going to be time independent. Okay, so for that, first condition is A will be AX. Second condition that we will be working with psi, which is a stationary state. Right, so for that psi we know then that d over dt of any arbitrary operator is 0, and that means that if we have I divided by h bar commutator of h a such function, it's also 0, then we can have h written as t plus v, okay, t p squared divided by 2m, and v is some function of x, okay, and then turns out that if we pick a operator as x times p, then for this expression where we have h and a commutator, we can write it as commutator of ta plus commutator of va, and this all thing will be 0, right, for any a. So it turns out if we pick a right a, then we get some insight into the way the average kinetic and average potential energy are related. And so again, skipping the whole derivation of the commutators, if you do this commutator with a equals x times p, then you will get the 2t values, average t, we multiply by 2. And if you take this commutator with a, again, x times p, then you get expression minus average of, can you see here? Yeah. X d over dx and then v. Okay. And so that gives you 2t average equals to x dv dx, right? Okay. Now what helps is that the potentials that we are working in quantum problems, say Coulomb potential and say harmonic potential is also like that, they are so-called homogeneous functions of variable x. So a homogeneous function f, let me just write it down. Functions of order k is defined like this. Okay. Okay. Right. And then there is a Euler theorem for homogeneous functions, and it states that if we have, say, a function, it can be functions of many variables, right? So general statement of the Euler theorem is that if you have x1, x2, x3, and so on, multiply by gradient of, it's a dot product with the gradient of that function, which are homogeneous function, then of order k, then you get k f of x. Okay? I'll show you that this is indeed the case. The proof is very simple. But using this on the expression like that, say imagine if your v is like v of x equals 1 over x, right? So then v of alpha x would be v of x into the power of minus 1, right? And so according to, can you follow? Okay. So this is order minus 1, the Coulomb potential, right? So then according to Euler's theorem, then x dv over dx would be minus 1 multiplied by v of x. Okay? And you can see with just direct differentiation, if you differentiate this, you will get minus 1 x squared, right, in denominator. Then you multiply by x, you will get back to 1x, 1 over x, and then minus 1 will be in front, right? So, and that will make, I'll erase the Ehrenfest theorem, and that will make us interesting connection that no matter what eigenstate you are in, if you have a kinetic energy calculated for that eigenstate, right, of the Hamiltonian, then two of these average kinetic energies will be minus the potential energy, okay, for the Coulomb potential. V equals to like 1 over x, right? Now, if you have a harmonic oscillator, V of x equals to kx squared divided by 2, right? Then V of alpha x is equal to k alpha squared x squared divided by 2, right? So this is alpha squared V of x, right? Then for harmonic potential, you have 2t average equals to 2v average, according to this expression again. Okay? So then we can cancel 2's, and the kinetic energy and potential energy for any state of a harmonic oscillator will be the same. And it's indeed so. For the ground state, the harmonic oscillator total energy is h bar omega divided by 2, and that means from this expression that quarter of the h bar omega is coming from kinetic energy and quarter coming from the potential energy. Okay? So this is a very useful statement. I guess if you want to write this down in terms of the order of homogeneous function. So the statement would be, if your potential is a homogeneous function of the kth order, then two average kinetic energies will be equal to the k average potential energies, right? And so all you need to know is what is the order of your homogeneous potential, okay? If it is homogeneous, of course, right? If it's not homogeneous, then you cannot use Virial theorem. But if it is, like in case of Coulomb, in case of harmonic oscillator, then you can use the Virial theorem and get the relation between kinetic and potential energy even without solving the Schrödinger equation.
The equation you have at the top of the board there, that's not considered the Virial theorem, or Virial theorem?
Well, it is.
We could use that even if our potential is not homogeneous.
That's right.
Yeah.
That's right, but then the trouble is that this part is not guaranteed to be an average potential energy. Right? So see, for the homogeneous functions, we go from the derivative back to the potential. Yes, indeed, you can use this. This is still, I guess, usable, but it's not as useful as this one because this has a physical meaning of a potential energy, right? This has meaning of something related to the potential, right? So this is not yet Virial theorem. This is, okay? Now, in the last 5 minutes, I just want to rationalize why, like this. You can either look it up later, but I'll tell you a little bit why this is the case. Euler theorem, essentially. Easy to prove. So now, imagine you have a function x1, x2, xn, right? And it's a homogeneous function of kth order. We will pick some 0 point in the domain of that function. It's just some constant point, right? And then we will write out of this function we'll build a slightly different function. We will build the x1 at 0 point multiplied by t, and then x2 at 0 multiplied by t, and so on, up to xn 0 multiplied by t. Oops. And since this is just a bunch of constants, we can call this as a new function of t. Okay, so that's the construction we're making. Out of initial function.
Sorry, what does that superscript of 0 mean?
It means it's a some value. It's essentially this. Okay, this is x and 0, x2. The coordinates of this point, right?
Okay, so it's some particular point.
At some particular point, right? Then, since we constructed this from homogeneous function, then we will have a relation that this is like a scaling parameter, right? And then it's t into the power of k from the f at the point x0, right? And then what we also can do is we can differentiate du over dt. And simply, since du over dt, you can differentiate this quantity. It is k, tk minus 1, and then the f at the point x0. Okay. Okay, then you can also, yeah.
Why were we allowed to just put those t's in? Or are we just saying let there be a new function?
Yeah, let's make a new function. Yeah.
Okay.
Okay, it's u. Okay, and then if we take this derivative at t equals 1, then this will be k fx0. Right? We can also take this derivative as a chain rule for this function, where we can call this our new variables x1, x2, they are not the same independent variables as here, but they are, now let's call them with primes, because they have some constant, right, multiplied by t, right? So then they're different variables, and they are also dependent. Okay, then we do the same du over dt operation as through the chain rules, and we have df over dx, I prime, and then dx I prime over dt. Okay, and then this becomes a gradient of f in these new prime variables, and this becomes essentially these constants that we kind of we froze them for a moment, right? And so this is gradient multiplied by xi0, right? And so this part is equal to that part, and that's the relation we were looking for the earlier condition, right? So that if we multiply by x and differentiate, we'll get k and then the function back, which is not differentiated, right? So k multiplied by function, and then this gradient multiplied by now essentially x point. Okay, so now we can do the same thing at every point x0 and obtain this relation essentially. Okay, so that's the Euler quick kind of proof of Euler theorem that allows you to have Virial theorem and allows you to go from the derivative of the potential for homogeneous function to the potential. Okay. All right. So those were some useful relations. We'll continue next week with more useful relations on operators. Okay.